So we're looking at the roots of complex numbers, which is actually probably not the best way to say it. You got to remember that we can represent everything as a complex number. So, or even our real numbers can be represented as a complex number. So the idea being that if we're looking for the nth roots of the complex number c, are the n solutions of Zn equals c. And I've copied that from the textbook. The nth roots of the complex number c are the n solutions of Zn to z to the power of n equals c. So what the idea of this means is it means that if we were doing this and we were looking at like z to the 4 equals, let's just say I for the minute, then this solution, this method here allows us to go, well, let's do 4 roots of I, and it should give us the values that solve this solution. So z will be these values. Now, I'm going to do an example in a minute, but these points are really important, and I will try to refer back to them. So there are exactly nth roots of c. So that means that if we have z to the power of 4, or we have the 4 fourth roots of a number, because we're looking at 4. So whatever number to the power here, or whatever value we got here is to the power, we're going to have 4 values from this. So if we were doing a cube, z to the power of 3 equals 1 would have 3 solutions that we could have. All right? So that's what it means there. If our complex number is real, so it's not a complex number, it's a real number, but if c is a real number, the complex roots must occur in conjugate pairs. So we already know that for real polynomials, so consider this, that if we have a polynomial, if it's real, we have conjugate pairs in this space, or they're going to be real. So the complex roots occur in conjugate pairs. If we have an odd power, remember, we can have a real root and 2 complex roots, but they have complex. If the complex number isn't real, the complex roots do not occur in conjugate pairs. So this means we would have a complex solution. The roots of z to the power of n will have the same modulus, which will be whatever the modulus is of this. So this one up here would be 1. So it'll be 1 to the 1 over n. So we're going to be using de Moivre's theorem to prove this. On an eigenplan, the roots will lie on a circle with the radius equal to the modulus that we've got. And then the roots of the circle with the radius equal to this modulus we're going to calculate will be equally spaced around the circle. If you join the points corresponding to the roots, you will obtain a polygon. Okay, so I'll try to refer back to these as we do this. So the first question, we're going to look at this example question, which is find the four fourth roots of 1 by. So we're looking at z to the 4 equals 1. And so if we rearrange this, because the first method of solution talks about by factorization, so we're going to look at z to the 4 minus 1 equals 0. And now we're looking at difference of 2 squares. So if you think about this, this is z squared minus 1, and then we've got z squared plus 1. All right, the solution for this top one here will be z minus 1, z plus 1, which we've got there. And then our other solution here is going to be, for this to equal plus 1, we're going to be looking at z minus I and then z plus I, knowing that when we factorize this as different as 2 squares, we're going to be minus I squared, which equals z squared plus 1. So that's going to give us the value we want. So our solutions for this are going to be z equals 1, z equals negative 1, z equals positive I, and then z equals negative I. Why are you not drawing? Okay, you've frozen up for a minute. All right, are you going to work for me now? No. All right, so that'll give us that for a second. Sorry, I don't know whether my pencil's gone flat or whatnot, but let's try now. Minus I. Cool, I'm back operating. All right, so if I was going to plot these points on the eigenplane, because we talked about here, the roots can be on the eigenplane, we've got these values here, and you will notice that 1 to the power of 1 over 4 is going to just be 1. So the modulus will stay 1. But if we were going to draw this, let me change colour for the axes. Our eigenplane will be like this, and I'll go back to blue for these. So we had one of our solutions was 1. So we're going to have a solution here. We had another solution that was -1. So -1. So this here, let's just call this one Z subscript 1. And then we had I as well as this one. So let's call this Z subscript 2. We've got Z subscript 3. And then Z4. You'll notice here these are all spaced quite nicely. They're 4 different values. They're all got a right angle between them. They're equally spaced. So these are the solutions. Let's go to the nth method. So the nth roots methods. This one here is more in line with our topic. So we've got Z equals 4. What we're going to do is we're going to change this to a complex root. Not a complex root, to a polar form. So 1 is equal to a modulus of 1 and then cis, an angle of 0. So that's what 1 represents. So 1, I'm just going to use this eigenplane. 1 is this value out here. Okay, it has a length of 1 and then it's got an angle of 0. But because of every time we rotate around, we could go and rotate around by 2 pi, we end back at the same point. We also need to go, well, plus 2 pi, and then times that by k. That's going to be our possible solutions. So now we've got De Moivre's theorem. So we're going to take the, not the cube root, but the quartic root of both sides. So we're going to have 1 cis, and now 0 plus 2k pi, or we can get rid of the 0 and just go 2 pi k. Now, I should have mentioned before, any of these numbers can be represented as a complex number. So we've got that for the moment, and this is to the 4. Now, using De Moivre's theorem, we're going to have 1 to the 1/4 root, cis, and then our rule states that we can have, and I should have specified, our rule here states that we've got 1 over 4, because that's the power, and then we're going to have times 2 pi k. Now, I missed a step up here. The moment I had the k, I should have specified that k can be any integer. So we've now got to this stage. Let's simplify this a little bit more. So 1 to the power of 1/4 is still 1. Anything to the 1 to the anything. And then we've got cis. And then this value here, if we look, we've got 2 over 4. We're going to be left with pi over 2 times k. So that's what it simplifies down to. And we're going to I now need to specify, I missed this bit here. We've got De Moivre's theorem up here. So we're now down to a value that we've got to pick values of k. So this z is going to equal these values in here. Now, when we're picking these values, we're going to pick our solution next. So therefore, z is going to equal 1. And we're going to have to pick values of k. So we go cis. So we're going to pick the values of k that we're going to pick are going to be 0, because it's the easiest one to multiply. So we're going to pick really easy values of k. So our first solution is going to be k equals 0. And then we're going to look at k equals 1. And then it's always good to go k equals -1. It gives us the opposite. And then we've got k equals 2 would be our... Now, we only need 4 solutions, remember, because it was to the 4th root. So we're going to have k cis, and then we've got pi on 2 times 0. And then our next one is going to be z equals cis pi on 2. And then our next one here is going to be z equals cis negative pi on 2. And then our last one here will be z equals cis 2 pi on 2, which will just be pi, 2 pi on 2. Now, these values here, knowing polar form like we do, we're going to have this one here, cis 0 is going to be 1, because it's got no angle. This value here, cis to the pi on 2, is going to be z equals I. And then we've got here z equals negative I. And then z equals negative 1. Now, one of the points we had was, you'll notice this is the same solutions we had from factorising. We had factorising up here. You notice these are all equally spaced out. So if we drew the point, so if we think about those points we've talked about earlier, some of these here, this would be a circle of radius 1 that would go around here, which links to this value here. If we join these, it would be a square, which is a regular polygon. So we've got a few different solutions there. But we've also got, just to take it back, we had originally Z4 equals 1. Any of these values, if you put them in your calculator and put them to the 4, they all equal 1. Now, I've sort of tried to rush through this. Have a go with these ones. I hope that all makes sense. Thanks.